So let's check out the reducibility of E2 reactions. Unlike substitution, elimination can result in more than one product. So we can take this when we have an elimination reaction, we need a base to take off a proton, and we'll get a double bond between these two carbon atoms. And we'll end up with a product that looks like this. If we instead take off a hydrogen that's up here, we'll make a double bond between this carbon and this carbon. And our product will end up looking, put the arrow there, very different. It'll look like that. And see, these are the blue carbons. And we'll put the green carbons here. So it just depends on which proton gets removed. Let's see. It's called regioselective because both compounds are made are produced, but in different amounts. The Zyphus product is the more substituted. And the Hoffman product is the less substituted. Usually, we make more of the more stable Zyphus product. So in our diagrams up here above, this is the Zyphus product, and this is our Hoffman. And this is the distribution. If we have a non-sterically hindered base, so this is just a base that looks like that, we make mostly the Zyphus. If we have a sterically hindered base, and this would be something like the T-butyl oxide, we get more of the Hoffman product. And if we even put even more bulky stuff around our base, we get almost all Hoffman. So let's look at these reactions and predict the major and minor products. So this is our halogen, and we're looking to see where we can take protons from. We need to find beta carbons that have protons. So this is our alpha carbon. This is a beta. This is a beta. And this is a beta. This one has no hydrogens. So we don't have any protons there. There will not be a double bond between these two carbons along this line. So we have two possible products. We can take a proton from here. If we do that, we'll get our double bond will be between this carbon and that carbon. Okay, let me change my color. And we'll do this one. If we take the hydrogen off here, we'll get okay, the double bond will be between this carbon and that carbon right there. So we'll get a structure that looks like that. This is going to be the minor product because it's the less substituted. It's the Hofmann. This is the major product. Let's go back to green. Major, and it's the Xiphus. Okay, the next one, we have this T-butyl oxide, and so this is a bulky base. Bulky base. And so we're going to favor the Hofmann product. So let's look. This is the carbon that is the alpha carbon. We have a hydrogen here that we can take off, and we'll end up with this product. We also can take a hydrogen from here, and we'll make a double bond between the two orange atoms, and we'll end up with this product. It'll have to stick up there, and it'll have a double bond there. Now we need to look to see which one of these will be the major and which one will be the minor. This one is the less substituted Hofmann. Oh, let me go to green. And it'll be the major because bulky bases favor the Hofmann, the less substituted. And this one will be the minor. And it's the more substituted Xiphus. Okay, so let's look at C. We can have a double bond formed between the two orange dots, whereupon we'll get something that looks like this. Or we can pull our proton from here and get a double bond between the two green carbons. And then we'll get something that looks like this. So this is the Xiphus, and this is our Hofmann. Can't spell. Okay. If we have a non-bulky base, like a regular base, we'll expect this to be the major product. This is the same compound, but with a bulky base, we expect the Hofmann to be the major product. So for each of the following reactions, identify whether you would use hydroxy or tadbuoxide to accomplish the transformation. So here we've got a chloride. So this is the carbon that's going to be involved. We can get a double bond this way, or we could get a double bond, we'll do it another color, this way. If we do it the orange way, we'll get the Hofmann product. The green way will give us the Xiphus product. So we want the green, so we want the Hofmann, we want the Xiphus. And so we'll want to use the hydroxy to give us the more substituted base. more substituted. Okay, here we're making the Hofmann product. Because this is the less substituted product. And so we'll want to use the bulky base. So we'll want to use the T-bute oxide. Okay, so we talked about Reginault selectivity. We also have stereoselectivity with our E2 reactions. If we have this compound, and we treat it with this irregular base, methoxide, we could get the major product, which would look like this, but we also get a minor product. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yeah. This is the major, and this is the minor. Okay. So we stay stereoselective because it makes both products in unequal amounts. That's why it's selective. We can have stereospecific, and that'll be in the next video.